any.
Okay.
So,
Okay, give it a try. Let's hope there are no glitches. Okay, let's see. Share screen is my understanding.
yeah.
Let me see how I can do that. Share screen. Well, I think it's actually working. Amazing, amazing. And can you see my screen?
Dazzled at the view.
Yeah, nice picture.
Ronda. Beautiful place. There's a bull ring right in the center of it.
Oh, okay.
And let me see here. Can everyone see that?
I can see a dog.
Yes. Okay, good. That's great. Let's see. I guess I should quantify this. Now you can see this. You see it. That's Grommet. That's no dog, by the way.
Okay, that's Grommet. Yeah.
Okay. And this talk, the title of the talk is Quantum Knots and Mosaics Revisited.
Yeah.
And let's see here. This is joint work with Luke Hoffman. And this talk is based on the following papers. Actually, maybe if I get out of full screen, let's see, how do I do that? Escape. Nope, that doesn't work.
There's something on the top right-hand corner. Should be able to do it.
I don't see it. I know what I have to do. I have to get out of this for a second. And well, I'm not sharing full screen. That's strange. All right, now let me share again. I apologize.
There's all these technical things. They always go
Glitches.
wrong.
We're all technically challenged.
Yeah.
All right, and now let's go back to this. All right, this talk is based on the following papers. All of these papers can be found on the archive and be downloaded there. The first paper is on quantum knots and mosaics. The second is related. It's quantum knots based on three-dimensional lattices. And also there's a paper on quantizing braids and other mathematical structures. And the talk is actually motivated by Mario Izzetti and Tullio Reggio. And they wrote a paper many years ago. In fact, Lou was the one who first told me about this paper on vortices and liquid helium-2 current algebras and quantum knots. I had the good fortune of spending a sabbatical there in EC and was able to work with Mario and Tullio. There's also a paper by Alexei Katayev, which is part of the motivation. I won't talk about that much, but it's related. Throughout this talk, to save many words, I'll simply, by knot, I'll mean either a knot or link. This way I don't have to repeat the same thing more than once. As an introduction, I'd like to mention that quantum mechanics is a really fascinating tool for exploring knot theory. That's from a knot theorist perspective. And of course, quantum knot theory is an interesting tool for physicists to explore quantum mechanics. For example, the work of Witten. Objectives of this presentation is to create, or objectives of doing this work, is create a quantum system that simulates a closed, knotted physical piece of rope. And to define a quantum knot in such a way as to represent the state of the knotted rope, that is the particular spatial configuration, the knot tied in the rope, and to be even more specific, to model the waves of moving the rope around without cutting the rope and without letting it pass through itself. To me, it's really interesting to be able to put a rope, in a certain sense, into a quantum system. The rules of the game are: find a mathematical definition of a quantum knot that is physically meaningful, physically implementable, and tractable, that is simple enough to be workable and usable. And if I go through these slides too quickly, or if anyone has any questions, please let me know. Okay, aspirations. We would hope that this definition, this work, will be useful in modeling and predicting the behavior of knotted vortices that actually occur in physics. And I won't be able to talk much about that in this talk. Outline, essentially we'll start with knot theory, and we'll basically translate knot theory into a formal rewriting system. And once we have the formal rewriting system, we'll see that it is equivalent to a group representation system. And at this point, we're actually done, because quantum mechanics is really group representation theory from a mathematical perspective. Okay, the placement problem, I think we all know about this. We have an ambient space, a group, an orientation preserving autohomomorphisms, and we look at the different placements, and the fundamental problem of knot theory is when they're equivalent. I'll go through this quickly because I think everyone knows about it. And here's, of course, the isotopy definition is also equivalent to that. Knot theorists work in shadows. They look at the shadows of knots. And a knot diagram is essentially a planar four-valent graph with labeled vertices. Okay, and then, of course, we have the Reidemeister moves that we're all familiar with. The Reidemeister 1 move, the Reidemeister 2, and the Reidemeister 3 move. And these are all local moves, which is important when we're trying to translate this into quantum mechanics. And finally, there's the planar isotopy move that's understood but frequently not discussed. And so we have essentially 4 different types of moves. And when do 2 knot diagrams represent the same or different knots? We have the famous theorem of Reidemeister. 2 knot diagrams represent the same knot type if and only if one can be transformed into the other by a finite sequence of Reidemeister moves. I find this theorem most amusing because it's meant gainful employment for knot theorists for over almost 100 years. Okay, as a preamble to knot mosaics, en route to defining quantum knots, essentially we encountered the following obstacle. And essentially knot diagrams and Reidemeister moves are a category, but quantum mechanics requires it to be a group. Okay, and here's the problem. And our way of getting around this problem, I use what I call the principle of conditional action. A Reidemeister move acts as the identity transformation if it cannot be applied. So it's defined in all cases. And this forces us to also adopt the principle that a Reidemeister move applied twice to the same object is the identity transformation. So in this case, now we're able to think of knot diagrams and Reidemeister moves as a group. And all Reidemeister moves are involutions, which will turn out to be very helpful. We could actually do this, create a huge Hilbert space as we will, of all knots. That would be too huge, but I think I'll leave that topic alone for the moment. Some interesting spin-offs from this that were unexpected. First one is that tame knot theory is a formal rewriting system, and I'll explain what that is in a second. It's in the automata theory, it's a context-sensitive formal language defined by a linear bounded automata. Knots are just meaningless strings of symbols. It takes the fun out of knot theory, I think, but knots are meaningless symbols, and Reidemeister moves are simply rewriting moves, grammatical rules. We need to do this in order to implement this. Okay. Spin-off 2, which is interesting, we've created an axiomatic system that completely captures and defines tame knot theory. which is a puzzling surprise. And of course, there are other models of knot theory. Liu's book on, let's see, Liu's book on knots in physics is one of them. And there are many other such things. All right, so I've talked about that. So let's talk about mosaic knots. Mosaic knots, and here is an example of one. I guess you can see the animation. I can't see what you're seeing. And so this is an example of a mosaic knot. We can define mosaic knots as possible. Let T denote the following set of 11 symbols, which we'll call mosaic tiles. Here they are. And essentially, they're really up to rotation. There are 5 different tiles. There is a way of doing everything I've done without this particular tile. I guess you can see that, but makes things more complicated. Definition of an N mosaic. An N mosaic is an N by N matrix of tiles with rows and columns indexed with zeros, 0 through N minus 1. Here is an example of a not so interesting 4 mosaic. Now I'd like to define what I mean by connection point. A connection point of a tile is a midpoint of an edge, which is also the endpoint of a curve drawn on a tile. For example, this has 0 connection points. This tile has 2, and this tile has 4 connection points. 2 tiles in a mosaic are said to be contiguous if they lie immediately next to each other in either the same row or the same column. And for instance, these 2 tiles are contiguous, and these 2 tiles are not. Suitably connected, a tile in a mosaic is said to be suitably connected if all its connection points touch the connection points of contiguous tiles. And for example, in this case, this tile is suitably connected. All its connection points touch connection points of contiguous tiles. And this is not, because some of its connection points do not touch connection points of contiguous tiles. Okay, in this way, now a knot mosaic is a mosaic with all tiles suitably connected. And this is a not so interesting 4 mosaic, which is not a knot. And here we have a 4 mosaic representing the trefoil knot. The tiles are actually very versatile. Here's an example of the figure 8 knot as a 5 mosaic. And the well-known Hopflink is a 4 mosaic. And of course, we can't do without the Borromean rings, which, excuse me, can be done as a 6 mosaic. As a note, excuse me, let Mn denote the set for some reason. Let Mn denote the set of N mosaics, and let Kn denote the subset of not N mosaics. And it's important. It's important to point out that these are finite sets for each N. That will turn out to be important. Now we need the concept of a cut and paste move. And a K mosaic of an N mosaic M is a K by K sub-mosaic of M. That's it. So here are some examples of 2 sub-mosaics. You can also take 3 sub-mosaics. Simple concept. Terminology, we have K sub-mosaic moves. A K sub-mosaic move on an N mosaic M is a mosaic move that replaces one K mosaic in M by another K sub-mosaic. And as an example of this, let's take a look at this knot. I believe it, yes, it is a knot. And let's apply a cut and paste move. We cut and we paste. So this is a cut and paste move. We can do that again. cut, and paste. So this is the move that's used. And notice if it's applied twice, we have the identity. So cut and paste moves are involutions. All right. Two different ways of thinking about case of mosaic moves. One is cut and paste operations in mosaics. But lest we forget, they work on finite sets, so they can also be thought as permutations acting on a finite set of in-mosaic knots. All such moves are involutions, hence, as permutations, they are products of disjoint transpositions, and we'll use that later on to compute a Hamiltonian. Okay, planar isotopy moves. Now we can get into the actual moves. We can represent all planar isotopy moves with tiles. First of all, to make the exposition simpler, I'm going to introduce some non-deterministic tiles. Here they are. And for example, this tile represents one of two possible tiles. It's non-deterministic, either one or the other. Each of the tiles above represents two possible tiles. Using that, we can define the planar isotopy moves, and essentially there are 11 of them, as shown here. And it can be shown this is a complete set. Of course, I should also mention that it's understood that each of the above moves depicts all moves obtained by rotating 2 by 2 submosaics by 0, 90, or 180 or 270 degrees. So for example, if we take this planar isotopy move, it represents 4 different moves. And moreover, each of the planar isotopy 2 mosaic moves represents any one of quantity n minus k plus 1 squared possible moves on an n mosaic. So it's a different move at each location. So there are quite a few moves, but they're all there. Okay, trying to get to the meat of the subject. Each planar isotopy move acts as a local transformation on an n mosaic whenever its conditions are met. This is the principle of a conditional action. If the conditions are not met, it acts as the identity transformation. Ergo, each planar isotopy move is a permutation on the finite set of n knots. And each PI move actually is, since it's an involution, is a product of disjoint transpositions. And now we can get into the Reidemeister moves. Here are the Reidemeister 1 moves. There are 2 of them, up to rotations and modulo the other statements. And Reidemeister 2 moves, 4 of them. These actually form a complete set. There's a paper by a PhD student of mine, Omar Shihab, proved this in the Journal of Knot Theory. Moreover, let's see, to define the Reidemeister 3 moves, which are a little complicated, we need some more non-deterministic tiles, and here they are. For instance, this tile represents either the left tile or the right tile at the bottom. So we have non-deterministic moves, and now we can synchronize these. Non-deterministic tiles labeled by the same letter are synchronized, and here we have 2 synchronized tiles labeled by A and 2 synchronized tiles labeled by B. And what does that mean? Essentially, if this tile is interpreted as the blue dots, then the synchronized tile takes the opposite color. And this is what we mean by synchronization. All right, Reidemeister 3 moves, and here there are. There are actually 6 of them, modulo rotations and location on the mosaic. So these are the moves, and this is well defined and forms a complete set of Reidemeister moves. Basically, each each such move, each R move is a permutation of the set of all knot mosaics. We can look at it that way. It's a cut and paste move also. In fact, each move, again, is a product of disjoint transpositions because it's an involution. Finally, we can define the analog of the group of all auto homeomorphisms, preserving orientation. We call this the ambient isotopy group, denoted by AN, as the subgroup of the group of all permutations on the set of knots, generated by all PI moves and Reidemeister move, planar isotopy moves. Finally, we can get to knot type. And to do this, we need a stabilization axiom. And so we define the mosaic injection, which injects n mosaics, n+1 mosaics. You can look at the definition, but a picture is worth 1,000 words. Essentially, all you do is to tack on a column of blank tiles on the right and a row of blank tiles on the bottom, and that is your mapping. So far, so good. And now we can define mosaic knot type. Two N mosaics, M and M prime, are the same N knot type, written in this way, provided there exists an element of the ambient group A of N that transforms M into N prime. And two mosaics, M and M prime, are the same knot type. Yes. Okay. But we have to add a stabilization condition. That is, two tiles are the same knot type if under suitable enlargement they are of the same N plus K knot type. This is an interesting axiom for knot theory because this really makes it adds a math induction to the theory. And without this, we wouldn't be able to capture anything, but it's a central axiom. Okay, now, before I talk about quantum knots, I thought it might be a good idea to just quickly review quantum mechanics. So I'll do that. And quantum mechanics in a nutshell, the state of a quantum system is a vector which is called by physicists a ket in a Hilbert space H. And physicists use Dirac notation. Essentially, you have a left delimiter, which is a vertical bar, a right delimiter, which is a greater than sign. In between that is a label, simply a label. You can do anything with it you'd like. A quantum state, psi 0 at time t0, changes into a state at time t1 via a unitary transformation U, that is given by the following expression, where U lies in the unitary group of all unitary transformations of the Hilbert space. So that's a state. In quantum computing, that's a computer instruction. Okay, and an observable in quantum mechanics is a Hermitian operator. So I times that is in the Lie algebra of the unitary group. And of course, we mean an operator which is invariant under the dagger, the adjoint, which is the same as this the conjugate transpose. An important observable is the Hamiltonian, which is the quantum mechanical analog of the total classical energy of the system. Okay, and time evolution of the state psi of a quantum system is determined by Schrodinger's equation. H with a bar through it denotes Planck's constant divided by 2 pi. And given two quantum systems, respectively, in states psi 1 and psi 2, the state of both systems together, the bipartite system, is obtained by taking tensor products. Finally, we come to the hardest aspect of quantum mechanics, that's measurement. And I can't go through all the details here, but You can think of this box inside as physical reality. We have no idea what's going on inside the box, and it's a black box. We have two inputs and two outputs. The top represents the macro world, and the bottom represents the quantum world. So this is input from the macro world, output from the macro world. I guess you can see my cursor, the bottom, and we have an input from the quantum world and output. The input from the quantum world is an observable, omega, a Hermitian operator. This represents the measuring device. The device is represented by this. And then that has a spectral decomposition of the following form. PJs are the eigenspace projectors, and lambda J's are the eigenvalues. And the input is a quantum state, the state of our system lying in the Hilbert space. And the output of this, read in the meter of whatever it is of the measuring device, is an eigenvalue of the observable. And the state immediately jumps into the projected state using projection operator of that eigenspace. The interesting thing about this is a probabilistic process, and quantum mechanics provides no insight into what's actually going on inside this black box. In fact, there's a great debate going on. In fact, before the measurement, you cannot assume that what you're measuring is actually there. According to Bell's inequalities, whatever you're measuring comes into existence at the time of measurements. It's crazy. I'd like to mention, for that reason, quantum mechanics is not well understood. And if you talk to physicists about it all the time, you'll end up with many arguments, many different arguments, especially over measurement. Quantum knots and quantum systems. So now let's define quantum knots. So we start with the Hilbert space of Mn mosaics. This is easy. Let H be the 11-dimensional Hilbert space with orthonormal basis labeled by the tiles so shown and so labeled. We define the Hilbert space Mn of n mosaics as simply the tensor product of all of those, n squared, because it's an n by n matrix. And this is the Hilbert space with induced orthonormal basis, the tensor products of all the tiles, n squared fold tensor products. I think, we identify each basis element with a ket M labeled by n mosaic and using row major form. So if this is our basis state, this is identified with the following matrix. Next, this is a long-winded version of the same thing. Essentially, we put everything in row major form. I'll go through this quickly. And then essentially we end up with the mosaic representation. Okay, the Hilbert space Kn of quantum knots is defined as the subspace of the Hilbert space of mosaics, n by n mosaics spanned by all orthonormal basis elements labeled by not n mosaics. Here's an example of a quantum knot. This quantum knot is said to be in the superposition of two knots at the same time. It's either the knot on the left or the right. It's both at the same time. And let's identify each element of the ambient group. We can identify that with a linear transformation, which turns out to be unitary because it's a permutation matrix. So each element is a permutation and simply permutes the basis elements. Hence, A of n is a group of unitary transformations. It's a discrete group, but it's a group of unitary transformations. Everything fits together. So let's take a look at this element. This is a quantum knot, the superposition of two different knots. And what we'd like to do is to apply a Reidemeister 2 move at these particular locations. Now, if you look carefully, you'll see that the conditions for the Reidemeister 2 move are met on the left, but not on the right. So in this case, when we apply a Reidemeister 2 move, cut and paste move, which is a linear transformation, the change is made on the left, but not on the right. And this is a unitary transformation. This is a Reidemeister 2 move of the state of the quantum system. We can go further. A quantum knot system is a quantum system having the Hilbert space K sub n as its space and having the ambient group A of n as its set of accessible unitary transformations. The states of a quantum system are quantum knots. The elements of the ambient group are the quantum moves. That's your Reidemeister moves and your planar isotopy moves. And so basically we have an infinite sequence of groups for larger and larger n's. Each is physically implementable. Everything I've said here, of course, is beyond the technology at this time. There's no reason why it cannot be done. Here it is again, and I'd like to mention something. Choosing an integer n is analogous to choosing the length of a rope. The longer the rope, the more knots that can be tied. And the generators in the ambient group are like knobs that one can turn to spatially manipulate the quantum knot so it doesn't pass through itself nor cut itself. Okay. Two quantum knots are said to be of the same knot type, N-knot type. It's the same definition as before, essentially, provided there's an element of the ambient group that takes one to the other. And they are the same knot type, provided they satisfy the following stabilization condition under suitable enlargement. And that essentially is the quantum version of knot theory. And we just saw this example. Essentially, this is a Reidemeister move that is a unitary transformation that transforms one quantum knot into the other. These two are the same knot type. Here is an interesting example. The ket on the top, K1, and the ket on the bottom, K2, are actually different knot type. Surprising at first, but you can see that there are very good reasons why that is the case. They're both entangled. The bottom one is an entangled state. Okay, now we get into the quantum mechanics. Hamiltonians, let's talk about Hamiltonians. Each generator G is the product of disjoint transpositions. So we're going to use that to create a Hamiltonian. So here we have it. What we'll do is we'll choose a permutation that re-indexes the indices, rearranges the indices, only the indices, not the knots, or not the mosaics, and so that it's in a canonical form. And now we, as a matrix, as a linear transformation, we see that this is the following matrix, where sigma 1 is the transposition matrix. It's curious to see that this is also the first Pauli spin operator at x, infinitesimal spin about the x-axis. And so now we have a matrix representation of this element of the group. And the next thing, let's let sigma 0 denote the 2x2 identity matrix. And so if we take the log of the matrix sigma 1, it's a multiple valued function. There's one different log for each integer s. We'll take the principal branch for simplicity. And in this case, the Hamiltonian, which is the log, that's a Hermitian operator, is given by this expression. Here's the corresponding matrix. These etas rearrange the rows and columns so they're back in the original order. So you can see that this is the structure of the Hamiltonian. And you can see what its eigenvalues are and whatever. Okay, using this Hamiltonian for the Reidemeister 2 move, let's do that and see what it looks like. We have a Reidemeister 2 move, and the initial state is given on the right, and the location of the cut and paste operation is indicated by the green square, dotted square. We have that the solution of Schrodinger's equation as a function of time is given by the following expression. We're rotating one quantum knot into the other. I'm assuming in this case I've chosen units so that Planck's constant is, no, I have Planck's constant in there. Yes, so I was going to assume that it is a Planck's constant divided by 2 pi is 1. I can choose units to do that. There's no need to do so. I already put the h bar in there. So this is an example. The Reidemeister move is a unitary transformation. Now things get interesting when you get to observables, because not invariants become quantum observables. So perhaps it's possible someday to devise a quantum experiment that computes a not invariant. What do we mean by a physically observable not invariant? Let's choose a quantum system, mosaic system. Then a quantum observable is simply a Hermitian operator. We know that. But which observables are actually not invariants? It's a good question. An observable omega is an invariant of quantum knots, provided it's invariant under the big adjoint action of the unitary group. Okay. And but how do we find quantum knot invariant observables? Theorem is the following: let K(n)(an) be a quantum knot system, and we'll let this be a decomposition of the representation into irreducible representations. Then for each L, the projection operator for the space, subspace, the representation space, is a quantum not observable. In fact, these observables form a complete set of observables for each particular N. Here's another way of getting observables. I'll start with a quantum knot system and let A be any observable whatsoever. Let star omega be the stabilizer group of omega. Then we can construct an observable by simply taking a representative of each coset, and we end up with a Hermitian operator, which is not observable, a quantum observable. Okay, it's interesting talking. I can't see a single face, but that makes it interesting, I guess. The following is an example of a quantum not invariant observable. Here it is. You can choose any not invariant you like, and you sum over the mosaic N knots, or only finitely many of them. And it could be the genus of the knot or the crossing number, whatever you like, the Jones polynomial if you like. Basically the energy levels are the distinct values of the invariant. Okay, it's gone faster than I thought it would go. I'd like to introduce you to the Quantum Knots Research Lab. We have the most advanced equipment around. And here is some of our advanced equipment. Some interesting calculations on lattice knots. And here's Gromit's quantum computer. And I think that's basically it. Are there any questions? I can't see a single face here. Hello?
Yes, we're listening.
Okay.
Gallery view.
Do you want to tell us about the Loop Fund?
The Loop Fund? Oh, that's a secret fund. It's called the Lomonoco Out-of-Pocket Fund.
Oh, I see.
Are there any questions? It's a strange way of giving a lecture. You can't see a single face at the time.
Once you're out of your share screen, don't you see some of our faces across the
Yes,
top
I
of
see
this?
you now.
Yeah.
I gave the entire lecture without seeing a face.
Otherwise, you're in broadcast mode.
Yeah, in broadcast mode.
I didn't quite understand when you said you took a Reitermeister move and made it involutive. I mean, the Reitermeister moves and the knot diagrams, they form a groupoid.
Yes.
So, and then you somehow made them into a group. I didn't quite understand.
All I did is extend the definition. I like to be, you want to take the composition of two functions, but it's not, or two maps in your groupoid, and that is, it's not always defined. So I added that definition. Essentially, the composition, essentially when it's not defined, you end up with the identity transformation. So you just extend the definition. You haven't changed anything about the moves.
If I understand correctly, Sam, you have two diagrams that are related by the Reitermeister move. So the Reitermeister move takes diagram A to diagram B, but it also takes diagram B to diagram A. So in the quantum state, it's permuting those two diagrams. Is that the way?
Right. It's
Okay.
permuting the entire set of not in mosaics into itself. It's a permutation.
Right.
But the point is that the way you look for a move, you're looking for it on a small sub-mosaic, and there's only one move possible because they've taken it to be very small.
Oh, I see. Yes, that's right.
Right, because if we were working with diagrams, then on a given diagram, there may be a lot of moves that you could do.
Yeah, but there are going to be a lot of mosaics which have this same thing. So you're going to have different mosaics where the move can be applied, but it will apply involutorily between different pairs.
It's going to shuffle. It's transposing. It's a
Yeah. Right.
You have a product disjoint transposition. So it's a big.
Right.
It's working on a lot of mosaics.
But
Can
it's
you-
not just the mosaics that it permutes, it's permuting the underlying basis of tiles, right? The tiles are forming a little space whose tensor powers give rise to the mosaics.
Right. It permutes the basis. That's absolutely right. And that's why it's a unitary transformation. It's simply a permutation of the basis elements. It's so the matrix corresponding to that is a permutation matrix, and that is automatically a unitary matrix. It all falls together.
Sam, you
Yes.
had one slide in which you had 3 unknots, and you said they were not of the same knot type. Could you clarify that?
Okay, let's see. I haven't thought about this in a time. Let me pull that up. 1 second. I guess I should share screen again. All right, and pull this up. And let me get there. Let's see. Where is that? These are the Reitermeister. Oh, I see. It's after that. Knot type. Let's see. Oh, wait a minute. I want quantum knots. All right. Where is it? Do you find it? Oh, here it is. Here it is. Good. Let me see. Here it is. There is no move which takes one to the other. No unitary transformation that takes the ambient group does not connect the two. I've forgotten exactly how I proved that. I guess one way of proving it, if you look at the first knot, it's an untangled state You look at the second knot, an unentangled state in the larger space of all mosaics, and the one at the bottom is an entangled state in the space of all mosaics, knot mosaics and non-knot mosaics. So that was essentially the proof of those. It looks strange. These are, you said there were 3 knots here, there are only 2. The top is one quantum knot, the bottom is another quantum knot, which is, strangely enough, both the left ket and the right ket at the same time in superposition. And
Okay.
if you were to look at this with probability, if you were to observe it with probability 1/2 squared, the coefficient, the amplitude squared, you'll see the left mosaic, and with probability 1/2, you'll see the right mosaic. And how quantum mechanics actually chooses what happens is still not understood and may never will be understood. Does that help, Dale?
Somewhat.
Let's see. How can I better explain it?
Your other slide, Sam, where you showed a Reidemeister move, illustrates an important aspect of that.
Oh yes, this is very nice. These are cut and paste operations. This is cut and paste geometry, yet we're doing a unitary transformation where this is a unitary operation. We're permuting the basis elements, and which is very interesting indeed, for me anyway. Let me see, let me touch this. And let's see, oh, this is not the move. Well, essentially you can see what happens. The move can be applied here because its conditions are met. The move cannot be applied here, but still I like it to be defined, so it's defined as the identity. And this defines the unitary transformation. And
sorry, Sam, when you say it's a unitary transformation, that means it somehow preserves some metric?
It preserves the length of the quantum knots. The quantum knots are vectors, and their length remains invariant under that operation, the unitary transformation.
So, sorry, so what's the length of this one then?
Oh, each is of length 1. Quantum mechanics is interesting. If you take the state of a quantum system, a vector, and if you multiply it by any scalar, any complex number, it's the state of the same quantum system. It's the state of the same thing. The state is not changed by overall phase changes. Actually, the state of a quantum system doesn't live in Hilbert space. Okay, it actually lives in projective space because it's the ray of all complex rays which contain through the origin, which contain this particular vector. I hope that's helpful. We're actually working in projective space, but to deal with the quantum operations, you have to work up in the Hilbert space, and that's what's done in quantum mechanics. A lot of interesting things are going on here. In the Schrödinger picture, the state of the quantum system is constantly changing. There's another equivalent way of looking at quantum mechanics, the Heisenberg picture, where the state of the quantum system stays the same, but the observables are what are changing over time. And those two ways of looking at quantum mechanics are actually been shown to be equivalent. There were 2 independent schools of thought, and they came up with 2 different definitions, and they were shown to be equivalent to one another. We see some faces again, I guess.
What are the bras?
What's that?
Is it helpful to somehow think of these mosaics as elements of a chain group, and the knots are cycles or something? I mean, you know, where the boundary is 0. because they're not, you know, the boundary, the points of the tiles cancel or something. Is that a way of looking at it?
I don't fully understand what you're saying. You're thinking of them as a chain complex. It's an interesting idea.
Well, since you have linear combinations of them, you could think of them as chains.
Yeah.
Oh, right. What would the boundary operators be in the chain complex? It's an interesting idea. Maybe you can make a homology out of this. I've tried, but I haven't succeeded.
Well, see, a comment. If you use the states of the knots in the sense of the bracket, then you can formulate the Kovanov chain complex in mosaic terms if you wish. You can.
That might be fun. That'd be fun. Yes, indeed. I haven't thought about that.
I presume the bras are just the corresponding same basis elements, just with bras surrounding them rather than kets. And so the inner product is just a delta function?
Well,
Yeah, the kets are
basically,
the dual vectors to the bras.
right. You got the dual Hilbert space. That's the basis of that. Are the bras. The kets
Yeah.
are the basis of the H space. And then your bracket product is a combination, a bra acting on a ket.
Yeah, so the bra acting on the ket is going to be 0 unless the corresponding mosaics agree identically or agree in some spot.
It'd be a complex number. It'd be some complex number. You have a bra is a linear transformation on the Hilbert space, and you're taking the value of the Hilbert transformation.
Yeah, but I'm asking how to evaluate the inner product.
The inner product is just simple. Well, there's one concrete way of doing it if you like to do that. You can think of the kets as column vectors and the bras as row vectors, and you take the inner product, the sesquilinear inner product of those two. You can look at it that way. That's very, very concrete. But you're just taking the bracket product is simply the evaluation of a bra, which is a linear transformation, the value of that linear transformation on a ket, which lies in the
I think Scott was asking you about the orthonormality.
Oh,
Yeah.
the basis elements are orthonormal. All the knots
Okay.
form
Okay.
an orthonormal basis. I should have emphasized that more. I had an underscore in one of the slides, but that wasn't enough, I think. You're using orthonormal bases, yes. So it's delta, it's a direct delta function. Well, it's a Kronecker delta in this case because it's finite.
Right.
Good point.
Are there any more questions?
Yeah, Sam, is there an interpretation of quantum entanglement in your quantum knot theory?
Oh yes, it's there. Everything is there. I didn't discuss quantum entanglement. It's a whole separate talk, but it's all there. You can have quantum knots which are entangled. Yes. Okay. You could start. There are many ways of defining that. You could start with a bipartite system, and you could form a basis of that system, and define what you mean by entanglement. Yeah.
Dale, a
Yeah.
comment. You may be thinking that there should be some relationship between topological entanglement and quantum entanglement. And there's a long discussion about that and some speculations in different directions about that point.
Been there, done that. Yeah, Lou and I have looked at that. If there is a relationship between topological entanglement and quantum entanglement, it must be very subtle indeed.
It's interesting that, I mean, we all know that the history of knot theory was studied by Kirkman and others, and Thompson, because they thought of it as entanglements in the ether, or knotted vortices. And of course, that's all rubbish. No such thing as the ether, so we'll forget about that. And now somehow it's come back.
It's great. More gainful employment.
Well, thank you.
It wasn't all rubbish, Roger. They eventually people began still study knotted vortices in fluids.
Oh
Just
yeah,
that
but this is
people
on the
began to
quantum
believe
level.
that the ether was rubbish.
Yeah, sure, yeah. But I mean,
Good point.
I'm thinking of this as the quantum level, you know.
Yeah.
Well, Sam, your talk has generated a lot of interest and questions. So thank you very much.
Well, thank you for inviting me. Good to see everyone.
Thank you, Sam.
Thank
Okay.
you.
Thank you.
Thank you.
I'll send you the slides.
Oh, that'd be good. Yeah, so send them to Lou. He's
I'll
the
send them,
keeper.
put them in our Dropbox.
Yeah.
I'll put them in our Dropbox. All right. Bye now.
Is there going to be another lecture?
Apparently, Lou is going to talk on Tuesday. Is that correct?
That's correct, yes.
Yeah.
I think you were suggesting that Sam might give another lecture. Is that right? You're right.
I don't know. I think about that one.
Think about it. Right.
Okay.
Are there
Thank
any
you.
other thinkers? Sergey? No? No.
You asked me to do another one.
Oh.
I'd be willing to. So let's have a correspondence amongst the three of us.
Oh, that would be great. So that would be in a week's time, would it?
Possibly, yeah.
Yeah. Good. Well, thank you all. And I'll finish here.